Good morning, everybody. So I will continue my series of lectures on zero-sum problems. And in the last lecture, which already was some days ago, I mentioned that I will sketch a proof in some detail of this result, which is somewhat of a generalized form of a result known for a long time, a conjecture result known for a long time under the name of Kemnitz Conjecture, which was proved 2003-2004 by Christian Reyer and somebody else simultaneously, Di Fiore. And this is in some sense more general in that it applies for P group, of course I would say. So it applies in particular to groups of this form, CP plus CP, or also CPK plus CPK. But also some other groups. So for instance, to which types of groups would it apply? One could have, for example, CP squared. And now I need to be careful not to, and so CP squared, and then one would have to add here a suitable number of powers of CP. Okay, maybe let's not do this, so I do not write something wrong. But this condition here is something which one can explicitly check since one knows the Davenport constant of P groups. So there are actually more groups than these that fulfill this condition. So, sorry for the back and forth. So, what would it have to be? So, I need here some values that sum to p squared minus 1, and so I could take Cp to the p plus 1. So, this should work out, and the Davenport constant is here p plus 1 times p minus 1 plus p squared minus 1 plus 1, and this should actually be 2p squared minus 1. So that's fine. So this would be a type of group where this also applies. So just to say that it's actually somewhat more general, but it's, of course, these are rather special classes of groups. But it's possible also, so to say, interesting from a systematic point of view that one really sees somehow the conditions, the properties of the group that are of actual main relevance. So it's not really something about Cp squared, but the argument applies if one has these relations among some constants. And the proof runs along similar lines as the proof for the Davenport constant, which we already saw in Professor Dangadurai's lecture. What did I already do related to this proof? I proved that this is a lower bound. So lower bound is done. And so it remains to show that it is an upper bound. And so recall that we had the following notion, N, G. So for G, a finite abelian group, and S a sequence, S G1 to GL, a sequence over G, where, and so G element, so we define N of G S K to be the number of all intervals in, no, not all intervals, all subsets in the interval, such that sum I in I, Gi is equal to So it's the number of subsequences of S with a given sum, but one needs to be a bit careful. So it's subsequences within the, it says, so more in an actual sequence sense, so it's not the number of divisors in the 3 abelian monoid. Excuse me? Okay, yes, thank you. Yes. I could, okay, thank you. Yes, I forgot this, sorry. So this is this definition, and then there's a generalization. So for H1, H2 in G, one can define the same with 2 parameters as the number of couples I in 1 L cardinality of EI equal to KI and sum I in I G it's not a good idea, let's write J. J. So here one does consider and they should be disjoint. Okay. So one has these definitions. So once one contains, one counts subsequences, and here one counts couples of subsequences. And now we will derive this result from a fairly technical result. So I'll write the technical result just down and then we'll discuss what it means. So technical result looks like this. So again, P odd prime G finite abelian C group with exponent G equal to n and the Davenport constant less or equal than 2n minus 1. Here I do not impose equality, and so let L be a parameter in 1n and S a sequence over J with length with a Davenport constant plus n minus 2 plus L less or equal than S, and the length of S should be strictly smaller than 4n. Then one has some conclusions. So before giving the conclusions, let's briefly look at which types of conditions we impose here. So the sequence should not be too short. In particular, so what is this? So here we approach, so if this is 2n minus 1, so then this is 3n minus 3 plus 1 at least, so the length of the sequence is at the very least, not at the very least, but so if the Davenport constant is maximal, here, so in our case it would be 3n minus 2, and if you recall 3n minus 2, this would correspond to the value of the eta invariant. So it's at least this long, and then y is strictly less than 4n. Strictly less than 4n. I already said it somehow the last time, that sometimes subsequences with some zero whose length is a multiple of the exponent are crucial. And in particular, we saw that if we can guarantee a subsequence whose length is an odd multiple of the exponent, then we can conclude for this type of group and extract a subsequence of length equal to the exponent here. So if I reduce to sequences whose length is at most 4n, there are not all that many multiples of n that are possible. So what are the possible multiples? Of course, the trivial multiples are n, but that's obviously fine. Then there would also be 3n, which is an odd multiple, which is also fine. And then there remains 2n. So the only thing we have to deal with is somehow a situation where all the subsequences with some 0 and the multiple whose length is a multiple of the exponent would have length 2n. So here are two conclusions. For each set that contains 0 and that is contained 0, L minus 1, one has the following sum I minus 1 to the I minus I S plus n I 3n minus I S plus sum. Now these are the sums. Here is sum in I, now a sum over the others minus I n I 2n minus I S is congruent to 1 plus 2 minus 1, so the inverse of 2, and S modulo n. So here this is the modular inverse of 2, which exists since n is the power of an odd prime. So I could also, I could just write it explicitly too, but I could just as well write instead of this n plus 1 over 2, then it maybe would be more intuitive what is meant, but in the argument it actually arises mostly as an inverse of 2. And so if we look at this formula, here I did not write anything here, and I did not recall it, but last time I said it already. So if I write nothing, 0 is implied. So that so here mentally one has to add zeros everywhere. So I do not write them everywhere. So this means a sequence of length I with some 0 and a sequence of length n minus I and some 0. So together they give a sequence of length n. So this counts something which actually is a refined count of zero-sum subsequences of length n. This is a refined count of zero-sum subsequences of length 3n. This is a refined count of zero-sum subsequences of length 2n. And here we have, yes, 2n, but 2n in total, but such that they split in a way that we like, because there we have a zero-sum subsequence of length n and another of length n. So basically, everything, these quantities give a contribution that would yield a zero-sum subsequence that is good for us. And what's not necessarily good is this part here. But as you already can see, via a good choice of this interval here, we can eliminate this contribution entirely if the L is large enough. If we look here, if the L actually attains n, then we can take here the I to be the full interval, and then this is empty. So then this part disappears entirely, and the only thing which is left is summing over certain quantities that give us all a subsequence that we want. So to say a zero-sum subsequence of length n or 3n, but 3n is also good. And then, so this disappears, and if any other quantity, any other capital N that appears in the formula is non-zero, that implies the result. But then one checks, not all of them can be equal to 0 because of this one here. So therefore, this formula is really relevant for the proof of this result here. And this verbal explanation is now complemented by something more formal. So one has S has a zero-sum subsequence B with B equal to n. B S has a zero-sum subsequence B with length B equal to 2n such that B has a zero-sum subsequence B prime with B prime in L n minus 1. Yeah. So one has it in at least one of these. That's what we want. That's what we want. And I gave an argument how one can deduce this in case that one chooses I, this maximal interval where this disappears, but if I is somehow, if the L is not maximal, but we can, if L is not equal to n, but we always can make this choice so that this part here becomes as small as possible. So if any of these n's here is non-zero, we're in case A. And so if all these n's here are 0, we get, because of this one here, that at least something here has to be non-zero. But this is basically exactly what is written here. It has a zero-sum subsequence B of length 2n, which has a subsequence with length in L n minus 1, which corresponds, so this is just another way to write this set here when I choose I equal to this. So then this corresponds to one of these coefficients here. So that's what one, so basically 2 is in a way a corollary, sorry, well, you know what I want to say, but I do not manage to get out the word now. So it is a consequence of this first one. So. How does one prove this result? Maybe I can get rid of this first. So now, always with everything under the assumptions that I imposed so far. So excuse me, somehow I got myself confused. Yes, okay, sorry. Yeah, so how does one prove this? So I will need a technical lemma, or rather, lemma B an odd prime G P group. Then one has two things. If length of S is greater or equal than the Davenport constant of G plus Pm minus 1, then the sum set minus 1 to the J n G I plus J P to the power M S is congruent to 0 modulo P. So this is the first conclusion. And the second conclusion is something similar with two coordinates. Not two coordinates, but two intervals. So second, if S is greater or equal, then the Davenport constant of G plus P to the M minus 1 plus I1, then sum set minus 1 to the J n I1 I2 H1 H2, here I have G M S is congruent to 0 modulo P. So that's more or less the same thing. In some sense, one can deduce two from one fairly quickly. I just somehow fix an interval here of this cardinality and then apply to the remainder the first part, and then I need to put everything together. So I will mostly give an argument for 1, and then 2 is mostly simulate somehow. One needs to be careful with the bookkeeping of the different intervals, but one takes out intervals of size I1 and then applies the result, this result all the time, and then puts things back together. So how do we prove the proof of 1? Or maybe I will write it over there. So I will remove this part here. So it mostly just says that if we can prove the first part, then everything is fine. So we'll recall this situation. And so prove lemma part 1. So also I should maybe highlight it's not strictly, and I mean actually not at all, an error that I did not make precise what the that the p to the power m is the exponent, because it's not necessarily, actually it's not necessarily the exponent of the group. In the argument, we will apply it with p to the power m, the exponent of the group, but it works just as well with any other power of p. So I can also take a smaller power of p, or say larger one, but I think a larger one will not always be useful. So it can really be whatever power of p. So how does the argument go? So it's the usual trick. Consider the map phi from G to a new group G plus E that is isomorphic to G plus CPM, and G is mapped to G plus E. So we introduce, so to say, a new coordinate, and then we have that the length of the length of phi to S, which is equal to the length of S, is greater or equal than the Davenport constant of this group. That's true because this is, which is always the Davenport constant of G plus P to the m minus 1. We don't need that the exponent, that the P to the m is the exponent for this to be true. It's always true. And then we have, from a result we already saw, that the sum over all, I think it's n g prime j Vs is congruent to 0 modulo p. So this is a result we saw in the proof for Davenport constant. That's true for G prime in G plus E. And I mean, what's the point of this? The point here is that now it's true for some G prime here, and but having added this additional coordinate here, we can work with this, because in some sense we don't really care about subsequences of Vs that have some G prime, but what we want to know about are subsequences of S with a given sum, and we want to say something in addition on the length. But in some sense this new coordinate here exactly tells us something about the length of the sequences, because for each element in the sequence we added an E here. So if the sequence has length 3, it will mean that the sum is, this E part will be 3E. So in some sense the element we indicate here helps to count, helps to control the length of the subsequent. Right. In some sense, if you want, helps to control is not really the right word. It imposes, in a certain sense, an additional condition, which will in particular imply that a lot of these terms here are 0. Because you see, there are, in some sense, there are conflicting conditions. Because we fix actually the length, but also this gives a restriction on the length, so they have to be compatible. So, yes, so just to indicate, so from here, it continues here. So. And I will get rid of this part. I already discussed it. Maybe later. So we're in the process of proving this. So for G prime equal to H1 plus I1E. One has that this NJ G prime phi of S is equal to NJ H1 of S if J is congruent to I1 modulo Pm, P to the power M, and 0 otherwise. We drop this E part because this E part measures the length of the sequence modulo Pm. So and if the conditions are compatible, it does not really add much. But if the conditions are incompatible, then we can conclude right away that such subsequences cannot exist. So thus, now we can, what do we do? Now we have this formula, and we take this formula and we drop all the zero terms. So we drop all the zero terms and replace this quantity by this quantity. Also note that here I passed from Vs back to S. So thus the sum J in Z minus 1 I1 plus JPM N H1 I1 plus JPM S is congruent 0 modulo P. Okay, and if we look, that's basically what we want. There's a small difference between the two formulas. What's the difference? The difference is that here we have J. Here too. That's the difference. Here we have the J, and here we have something else. So since P is odd, we have that minus 1 to the JPM is in fact minus 1 to the J. So we can replace. So we can drop this PM here, then we would still have the I1 here, which is also not here. But it really, I mean, it doesn't matter because we can just we can multiply by minus 1 to the I1, and it does not change anything. It just, I mean, what's crucial is that the signs alternate. So the signs alternate with the J. If we start with a positive or a negative sign, it doesn't matter because we just want in the end it's congruent to 0. So this ends the proof of this lemma. And now for the proof of the technical result. So that's the lemma we proved. And maybe I will do something here. So I proved the first part and I said the second part will be similar, but for future reference, the second part will be more relevant. So I will replace the first by the second part. So it was plus I1 here, and then in the conclusion I needed here I1, I2 plus, and here it was H1, H2. So this is the second part, which we will actually use. So now we give the proof of the technical result, proof of the technical result. One can observe that it's basically consequence of this one is 2 times 0 minus 1 I is S modulo B. And for K in some J Z N K J N K S is congruent to 0 modulo B. So that's what we have here. And since S is strictly less than for N, we can use this for K equal to 0 to get N 0 0 S minus N 0 N S plus N 0 to N S minus N 0 N S is congruent to 0 modulo B. And now here, and now we substitute this. So here, for this we can because we actually have the term here, so it's I mean we need to rewrite it slightly. So from this we get that 2 minus 1 plus n. So this one here is actually, this is 1. That's also relevant. So the value of this is 1. 1 n 0 n s plus n 0 to n s plus, now here sum 1 n minus 1 minus 1 I n I to n minus I s. So this is, all this is congruent to n s modulo p. Okay, so this is this, and this corresponds to the case that I is equal to 0. This corresponds to the case that I is equal to 0 if we multiply by the inverse of 2 and put the 1 on the other side, we get this on the right-hand side. And on the left-hand side, what is left is that we have all these sums. We have all these sums here. And I forgot, sorry, I forgot to write the term here. 3n. Yes, I forgot to copy it. So this is this one here. This and this one here, so and we also flipped it. So one gets this, so this is the case. This is the case I equal to 0 of the result, and for the general case, note that by the preceding lemma we have that n minus k s plus n k 3n minus k s is congruent to n k 2n minus k s modulo p. And then use this for each. Okay. So one has this condition. So this is again from this lemma here, and one switches, so to say, one takes, so to say, an I here and puts it on the other side and uses this congruence. So this more or less ends the proof of this result. So there are certainly not all the details there, but I hope still that it somehow conveyed the spirit of the argument. So it's, in some sense, what's to retain from this argument is that it's a non-constructive argument. And we do not really get the subsequence. We count modulo p. And so we give some arguments, and then we know it's unavoidable. There must be such a subsequence, otherwise our congruences do not work out. But it's in stark contrast, for instance, to the proof of the Erdős-Ginzburg-Sieve theorem that I gave using the Cauchy-Davenport theorem, where one added the sets and somehow the conditions, the sets grew, and one saw at the end I can represent everything, and I can deduce the existence of the sequence. So this could be, this is somehow a more organic proof, because I can somehow in each step at each step on the way I can somehow trace the progress, and in particular it's easier to derive the structure of the extramal examples from this other type of proof than from this proof. So if one wants to deduce from this proof the structure of the sequences that are one shorter that fail, then this is not at all clear how this ever could be done. And indeed, so it's not known, the structure of the extramal examples in this case, even for the case, the simplest case of CP plus CP. I might say something more about this, although there are results in this direction already known. So now the time is already somewhat advanced, but I will continue with some more results on the Davenport constant and the Erdős-Ginzburg-Sieve constant, and I will continue with this in the afternoon. So today I will give a second talk, which is the first talk of the afternoon session, and so it maybe does not matter that much if I stop somewhat in the middle, so I will maybe just clean part of the blackboard quickly and continue with some more results. So in particular, so what do we know now about the Davenport constant and the Erdős-Ginzburg-Sieve constant? What do we know about those? So further results on Davenport and so it's known for cyclic groups, for groups of rank 2, for groups of rank 2, and for P groups in case of Davenport constant. For the Erdős-Ginzburg-Sieve constant, we do not have an argument for general P groups. We just gave here an argument for very special groups of this form. But somehow, can we maybe sometimes something which was already said at times, so one can conclude from CP plus CP to general groups of rank 2, and we saw the argument in detail for the Davenport constant. The question is, can we somehow leverage this type of argument for other groups, or is it limited to groups of rank 2? And for the most part, it's unfortunately limited to groups of rank 2 if we want exact results, but there is still at least one case where one can use a similar type of argument. And so we can also obtain the exact value for rank 2 like group. And there's no exact definition to rank 2 like groups. So it's just in some sense similar to groups of rank 2. So for instance, one might say this type of group is similar to a rank 2 group. So one thing that is typically the case is that the exponent of the group is very prominent relative to the rest. So at least the exponent squared should be larger than the order of the group. So this is one feature of rank 2 groups, and this is an important property, but that's not all one needs at each point. So, and in particular, one can show the following result, which in one form or another is known since a very long time, mostly since the beginning of the entire business of studying these constants. Maybe not in this exact form, but so let H, so let G equal to H as K be a B group. The import constant of H equal to K. Then the constant of H plus CPK n is equal to what one expects. So this, what was this T star? So this is the standard lower bound for the Davenport constant. And I think I can just write this here with lesser equivalent, because otherwise it doesn't even really make sense that I write the result like this. So, and one can also write this equivalently as it's d star of H plus pk n minus 1, which then is also, since this is the B group, so it's also dH plus pk n minus 1. And so then these are for n in n. So it's true for any n in n. So not just, so we pass from P groups here, so away from P groups. So this is not the P group anymore. And how does one show this? The argument is a so-called inductive argument, which we already saw from time to time. So first we can show, or actually we saw this already. So I will finish briefly. So started slightly late, so I will continue this. So one can show this. So eta invariant, this means a zero-sum subsequence of length at most the exponent of the group. So now, of course, one can show this. Now, the case n equal to 1, I mean, this is clear. I mean, there is literally nothing written here. If nothing new written here, if the n is equal to 1. So assume n is greater or equal than 2. And now one notes, note that n k has bk minus 1 is equal to n plus 1 minus 3 bk plus 3 bk minus 1. So of course this is n minus 2. And now let K be a cyclic subgroup, a subgroup, a subgroup, a subgroup, a subgroup of H plus CPK n such that the quotient H plus CPK n by n is isomorphic to this original, no, I did not call it G, so H plus CPK. And yes, and there's this. And such one has this, and now consider a sequence of lengths. Consider a sequence of lengths then what constant H plus CPK n is a sequence S of length this and its image in this quotient group here in its image in, let's write it like this. So then it has at least how many? N minus 2 and one more. No, n minus 2 at first, then one more of length at most bk, and then we have 2 bk minus 1 left, so still one more. At least n zero sum subsequences. So, and these yield n elements in K, which is Cn, and so we get a zero sum sequence in K, and combining these together yields a zero sum subsequence of the original sequence. So maybe this was a bit quick at the end, but I do not want to go too much over time because then it's also a break to the next talk. So just to summarize, so we can use the arguments used for rank 2 groups for slightly more general groups. But, and this is just as an introduction to the sequel, a crucial property is here that the eta invariant is not too large, because otherwise the argument breaks down. But I will come back to this in the afternoon.